So I'm speaking on behalf of a group that worked on how to automate training data for generation of automated workflows. And the goal of this group is to train a model to be the bioinformaticist of the future, and essentially replace myself, replace Moloch, replace all of us. You're welcome, Moloch. So the goal is to do that. And in order to achieve that, we know there are several training techniques that will get us there. And I'm going to go over those briefly, but we're going to need the right kind of training data for that, right? And I'm borrowing from this paper because I like this particular diagram where we can differentiate different kinds of training. So there is supervised fine tuning, where we could basically look over Moloch's shoulder, copy him, and this is some kind of behavioral clonal training. This is like watching what he types into his keyboard and then continuously learning from his expert demonstrations. That works okay, but it's not super great. It's not as good as some of the other forms of learning that allow for better generalizability. And in particular, in this paper, they show that, for certain classes of problems, that really fails. So then you have reinforcement learning, where you have a reward model, where you say, hey, I'm going to reward you based on how good or bad your answer is. And this is the classic paradigm that you may have heard of with AlphaGo, with DeepMind, where if you win the game, you get a reward. If you lose the game, you don't get a reward. And you want to reward that behavior. So you're going to learn a policy of behavior. That is, you're going to learn a policy of actions that lead you to that reward. And that has been shown to be really robust as a way of operating. It is something Arvind presented a little bit on in his preference optimization for proteins. And it is a way in which we could learn how to perform the right bioinformatics actions, that is, the right data manipulations, the right tool calls, in order to perform some final task, like answer a question. And that's what we're really after. And this particular paper goes over a new proposed way of doing this, but there are lots of flavors of RL. And the main takeaway I want you to have is that with good question answer data, with those good labels, we can train an LLM after lots and lots of compute to perform tasks in a more generalized way. Okay, so we started off by providing annotation instructions for experts. And this is something that comes from our experience in doing this with a physics community. We recently published a paper where we gathered about 40 different assistant professor, postdoc / physics experts. We got them to essentially work through very, very, very hard physics problems that essentially require significant amounts of time and research. We got them to do this by taking one of their recent papers, changing a little bit about what they were calculating or the system they were working on, and then essentially making them write a whole nother paper, but a whole paper that's not interesting. So it will never be a pollution problem. It's like a made up problem. And so the objective is really you have to present the problem with all the data you need to solve the problem. We ask that you break down your thought process so that you provide some subtasks, and then you provide an answer. And that answer should be something that's very difficult to guess and should be something that requires you to compute to that answer, so that the LLM will be forced to do that. So as an example of that, what we started doing is we started on day one getting people to actually do this manually. So this took actually day one and day two to some extent to build these manually and to get everyone to understand this and to also build the format for this. We have tens of examples of manually built out ones, and Anusha's not here. She provided the majority of the manual ones. And this is the format, right? You have a question. What are the first 3 digits of the effect size of the top B fragilis? And it's cut off here because it should wrap. But the effect size of the top B fragilis taxa that correlate with deficient mismatch repair colorectal cancer versus non-cancer samples. And the answer is 324, because those are the first 3 digits that come up in the answer. And then you have to specify what reward function, what grader you're going to use to grade this. And in this case, it's an integer exact match. And that's the problem. Then we also provide a sub-problem which can help the trainer along, especially when it's having difficulty in the initial phases of training. Bin the reads into OTUs. How many OTUs are there total? And so that's like an intermediate step, and it has a grade. And so there's a way to get an intermediate reward and to know that you're moving in the right direction. Inside of this, we also have to provide some information about what files are available. So we either need to provide a workspace ID or we need to provide files with a file description and a checksum, and also a set of tools, because the tools in bioinformatics are also moving all the time. And so because one version of an OTUing tool may differ from another one in terms of what it outputs, we need to specify which tools are available for this problem in order to solve it. In this case, we're specifying BVBRC. We're imagining there's going to be a data MCP, and we have access to Python. So, after understanding manually what we were going to do, we started figuring out how could we cheat the system, because manually annotating these is really, really awful. It took us a long time to produce very few examples, and those examples are not even validated because we actually have to put together the files and download the files and run everything to make sure that we get the same answer as we expect from the paper. So we had some work where we took scientific publications, we extracted the questions from that scientific publication. We tried to identify the tools that were used to answer that question. We asked the LLM to identify subtasks and to identify then QA pairs at the end. And then the very end of that, we need to validate those tool runs and then have validated QA pairs that will hopefully work. Now, this side over here with the validation has not been done yet. That requires some time. And in between, we imagine there's going to be a semi-manual curation task where it would be nice to have people look it over and make sure it makes sense before we try to validate. And then as a very last thing that we did was we also, in same workflow-ish, but instead of scientific publications, we took traces of user logs and tried to use those to ask the LLM to imagine what kind of queries these tool calls were being used to answer, and to essentially fill out the same format from examples of user log information. And that would run through the same system, and that's how we envision moving forward in the future. And that's it.